Hi, we are Group 10, and this is the next level of coffee. Our project goal for this term will be to create a process flow diagram complete with operating parameters for each piece of equipment that will be determined through small-scale experimentation. In other words, we will design an industrial process flow diagram for creating coffee, and instead of randomly choosing parameters for each piece of equipment, such as temperature and time for brewing or filtration level for water filter, we will be performing experiments to determine the best setting for each machine. This will allow our diagram to be backed up by real-life data that we had each individually obtained, making the diagram much more practical than a random one would. Now we will discuss the experiments we had completed thus far.
In our first experiment, we planned and executed a method to test the relationship between the concentration of coffee and the average conductivity. To do that, we began by weighing a certain mass of coffee and putting it in a measured volume of water. After some dilution, we begin by emptying half the original cup of coffee into the next cup and finish the other half with water. We start to do that consecutively for 9 cups. In this process, the concentration of each cup is halved, with some uncertainty errors. After this, we measure the conductivity of each cup 3 times, and through this, we can determine the relationship between concentration and conductivity, which can be used later when we have one of those parameters and we want to see what it corresponds to.
In this experiment, we wanted to investigate the effect of temperature on the concentration of coffee by first measuring the conductivity of the solution in microsiemens per centimeter at different brewing temperatures and converting it to concentration in grams per liter. As shown on the graph, concentration varies directly to temperature. The ideal temperature identified from the experiment was 75 degrees Celsius. Since the concentration did not increase significantly with the increase in temperature, this temperature was chosen to save energy during brewing.
The third experiment was centered around finding the ideal amount of time coffee should be steeped for. Testing was completed using 4 different times over the course of 2 trials. The coffee was allowed to cool before we tested for its conductivity in order to ensure that our results would not be swayed by temperature. After around 200 seconds, the data began to plateau, telling us that allowing the coffee to steep longer than this would not have any effect on the coffee's conductivity and would therefore be ineffective.
In this experiment, we varied the mass of salt added to a fixed volume of water. We used the water to brew coffee, 2 trials pictured on the right, and recorded conductivity in microsiemens per centimeter. The conductivity was then converted to concentration from the equation on the calibration curve and a graph of concentration versus contamination plotted. As the mass of salt increased, so did the concentration of the brew. That is, they were directly proportional, as depicted on the graph. However, since salt is a conductor, when dissolved in water, it is unclear if the concentration of coffee in the brew is actually increasing or if the salt is adding to the conductivity of the solution. We found that a better contaminant would have been sugar. Even so, we concluded that water contamination had to be taken into account in the process flow diagram, hence the water filtration system.
In the fifth and final experiment, we tested how different masses of coffee mixed with the same volume of water affects the conductivity, which is directly related to concentration as we have seen in previous experiments. We can clearly see from the graph above that there is a direct relationship between the mass of coffee in grams and its conductivity in microsiemens per centimeter, but only until a certain point. After this point, it starts to plateau, which could have been shown more clearly if the range was expanded. After research, we found that our conclusion was backed up, but it needed to be proven with a wider mass range. The reason for this is because at a certain point, no matter how much mass of coffee one adds to the filter paper to start brewing the coffee, not all the coffee particles will be brewed. Because the water can only go through so much particles of coffee while being filtered, because the size of the filter that we're pouring the water through is not infinite. We determined that the ideal ratio was 10 grams of coffee to 6 ounces of water.
Many aspects of our process flow diagram are influenced by our experiments. The main portion of our process that has been influenced by the experimental data we collected is the coffee brewer. For instance, experiment 1 helped us find what the best ratio of water to ground coffee is. The calibration curve showed us that the more concentrated our coffee is, the more conductivity it has, meaning its taste will be enhanced due to it being more bitter. During the second experiment, we found that the ideal brewing temperature was roughly 92 degrees Celsius. Experiment 3 allowed us to test how different brewing times affect conductivity. This again affects the taste of the coffee, and we found that the time that produces the highest conductivity is roughly 210 to 390 seconds. After completing further research, we decided that the ideal amount of time would be roughly 5 minutes. Finally, the fourth experiment provided us with data that a higher ppm, or in other words more contaminated water, would produce a more concentrated coffee. We could not, however, attribute this as being a beneficial since the surplus in concentration could be due to harmful minerals staying in the coffee. After researching the different filters and methods industrial companies use for their water, we came to the conclusion that an ultraviolet disinfection system would be best. This system would ensure any minerals that could be harmful to the health of our consumers would not make it through to the brewing process. The system uses a combination of different types of filters, including backwashing, cartridge, and granular activated filters. The numbers we use for the coffee roasting machine and coffee grinding mill have not been tested for, but rather have been taken from reliable internet sources and large-scale coffee producers. The final product we plan to produce is a bottled iced coffee. We believe this product will be easier to bottle, shelf, and produce, and iced coffee products have also been seeing a lot more popularity in recent years, notable products being Starbucks branded iced coffee and La Colombe canned iced coffee. The first segment of our PFD is the coffee roasting machine. As mentioned in the previous slide, all aspects of this machine's parameters were found through research. Our team found that for a machine with a capacity of 30 kilograms of beans, the ideal operating temperature would be 200 to 210 degrees Celsius. This range is ideal due to the beans releasing oils that bring out their aroma and flavor at roughly 204 degrees Celsius. Roasting the beans at a higher range than this could risk burning them and being left with a coffee that tastes burnt or extremely bitter, while under roasting the beans could result in a coffee not being as flavorful. We also found that the beans would need to roast in these conditions for around 20 to 25 minutes. We believe running the machine close to the lower end of this range is better, as roasting for shorter amounts of time produces a lighter and less bitter brew. A machine of this size and capacity could produce around 90 kilograms of beans per hour on average.
From our initial research, we found that a coarse grind, that is a particle size more than 2 millimeters, would decrease the grinding time, but the coffee grounds would have a smaller surface area to volume ratio, whereas a smaller particle size, that is less than 2 millimeters, would have a longer grinding time and a greater surface area to volume ratio. After extensive research, we concluded that a smaller size would be best. This is far more beneficial when considering the chemical process that coffee beans go through in the roasting machine before grinding. When the beans are roasted, they release coffee oils that give them their unique flavor profile. The diffusion of oils into the brew would be more efficient if the surface area is increased, that is, grinding the beans to approximately 0.05 millimeters to 2 millimeters. Therefore, it benefits us to use the smaller particle size. The Ditting KF1800 was chosen as a model because it fit the particle size parameters and was able to output 12 to 13 pounds per minute.
Regarding the water filter of the process flow diagram, as we can see, the inputs are going to be contaminated water, and the mass of this contaminated water is 628 liters. And when that contaminated water goes through a water filter system, which has several smaller filters inside of it, each with the duty to remove certain items from the water. So, for example, reverse osmosis handles fluoride removal, and then we have ultraviolet disinfection system, which kills bacteria, cysts, and other microorganisms. There's a lot of different types of filters: backwashing filters, cartridge filters, granular activated carbon, GAC. No one single filter can remove everything from water, but through a filtering system, pure water can be yielded by using a combination of treatment methods. And the mass of the filtered water in the output with desirable pH is also going to be 628 liters. The overall contaminants removed are going to be sand, silt and sediments, chlorine and chloramines, fluoride, pesticides and other chemicals, iron and sulfur.
Now for the brewing machine. Through research, we had found a range for each of the parameters at which a majority of industrial coffee brewers operate at. For temperature, the range which we had found was between 90.5 and 96.1 degrees Celsius. Looking at the pros and cons, a higher temperature would draw more power, but guarantee the coffee is never under-extracted. A lower temperature would save on power, but from our experimentation, we know we would still be able to produce a fully extracted beverage. So for this parameter, we had chosen to brew around 90 degrees Celsius. For the time parameter, we had found similar pros and cons. A higher range at 7 minutes would guarantee maximum extraction, but looking back at the experiments again, we found that only after 3.5 minutes the coffee would be fully extracted, meaning that choosing a lower time range would work to our benefit. Lastly, we found that an industrial scale brewer will produce roughly 120 gallons of coffee per hour. Once the coffee is brewed, we plan to use a cooling tower for the already brewed coffee in order to cool it down before it gets sent to packaging. A cooling tower takes in hot water and uses sprinklers in order to allow the hot water to be exposed to dry air as seen in the red part of the picture. Then once it has all settled down to the bottom, the heat is sucked out of the tower using a fan and sent into the atmosphere. By using a cooling tower, not only will the hot coffee cool down to room temperature, but it will also increase the concentration of the coffee itself. Through the cooling process, water will be evaporated, and thus increasing the coffee to water ratio. Having such a system will also guarantee quality of the product, making sure no coffee produced will ever be watery. This will work complementary to the brewing machine because if concentration can be increased in the final step, it shouldn't be a concern that extraction is too low in the previous one. Since this project is all about coffee, we thought it important to research the international industry of coffee to try to understand how it works a little. We started by looking at where coffee is produced. As you can see from the graph on the right, Brazil is by far the largest producer of coffee. Following them is Vietnam, then Colombia. Vietnam in particular interested us because it is not usually the place people think of when they think coffee, and that is actually because of the type of bean they produce. As you can see, Vietnam produces mostly Robusta beans, which are easier to grow but are very dark and bitter and sometimes considered lower quality. This means that most of their beans go towards making instant coffee. Arabica beans, on the other hand, are considered high quality and especially in the Colombian climate are considered some of the best in the world. Now, aside from this, something interesting we found about the coffee industry is that many times it's considered a monopsy, meaning there are few buyers and many sellers, essentially the opposite of a monopoly. Large companies like NKG and Ecom buy raw beans directly from farms to sell wholesale to slightly smaller but still large distributors. Sadly, in such a market, the farmer is the one who loses. In many cases, they will only see about a 2.5% return in the final retail price.
When researching potential markets, our team found that 3 brands stood out when it came to selling coffee. McDonald's led the pack as the largest seller of coffee, closely followed by Dunkin' Donuts and Starbucks. We believe that a combination of the company's low prices on their product and the ease of access that drive-through locations provide are what led to their success. Although we plan to bottle our drink and ship it across the country to be stocked in stores and small coffee shops, replicating the success of these businesses could be a step in the right direction when it comes to our future. Of course, when it comes to expanding past the scope of the US, 2 countries stood out in coffee consumption per capita, both the Netherlands and Finland. The other countries that were below them by quite a large margin were all located in Europe. Through this data, we can infer that the first place we should expand to internationally would be Europe and then move outward from there. Looking to invest in a Keurig product could be something exciting as well. The largest Keurig brand, Keurig Green Mountain, captured 9.9% of the coffee market in 2019 with their K-Cup product.
So this is just a slide about all the references and links and sources we had used for the culmination of this presentation that hadn't already been included on the slides. This concludes our presentation. We really hope you learned something interesting, and on behalf of Group 10, thank you for listening.